In the course of a day, we deal with many lists. Here is a shopping list. So what do we want to do with a list? Well, we want to add to it sometimes. Maybe I forgot to add tomatoes. So I put them on at the bottom of my list. Oh, I forgot to add eggs, but I don't want to put them at the bottom. I'm going to put them after milk. Why am I going to put them after milk? Because they're often kept where milk is. So if I take my list to the grocery store, I've got my eggs and my milk together, so I can add it in the middle. I could add something at the beginning. Maybe I want to make sure that I don't forget coffee. I'll put that on the top. So I can add at the beginning, I can add at the end, I can add someplace in the middle. Now, when I'm shopping, I maybe want to delete some things. So I bought my oranges, I can cross those off. I bought my peanut butter, I crossed that off. I've decided I don't want to buy cheese anyway, so I'm going to cross that off. So I delete these things as I buy them. And, oh, I've crossed everything off my list. My list is empty. So maybe I want to know when I have nothing left on my list, or possibly how many things I have left on my list. I want to be able to delete things. I want to be able to add things. These are the operations that I want to be able to do with a list. Well, you tell yourselves, that's fine. We could keep this as an array. And surely we could. We can keep this in memory as an array. But you remember that an array has to be in contiguous spaces in memory. And by contiguous, we mean one element immediately after the other in memory. The reason for this, and some of you who've done 345 with me will know this, is because every element in this array is the same type and therefore has the same number of bits assigned to it. So let's imagine we've got 16 bits for each, or 2 bytes, 16 bits for each of these elements. So if I want to go to element number 3, where is this in memory? It's the address of the first location is kept in memory. And then because I want to get to number 3 over here, I take the address of the first one and I add to it 3 times the amount of space each one of these needs. So I just said each one of these takes 2 bytes, so 6 bytes I would add to it to take me over to here. So with an array, the address of each individual element is not kept. Just the address of the very first one, and then it calculates where to find the other elements. And because this is how arrays are handled, the array has to be all stored in memory, one element after the other, no spaces in between. With a list, we can keep our data in odd spaces here and there all over memory. We do not have to keep it in contiguous spaces. So we could have one item over here, another item here, another item over there. It doesn't matter. Just as with an array, we keep the address of the very first element in the array, with a list, we keep the address of the very first element in our list. But how do we get to the next one? With an array, it's easy. You add the number of bytes to the address of the first one, and that takes you to the second one, etc. But you can only do that when they're all stored in a line like this. When they're all over the place, you have to have a different method. And with lists, what we do is we keep the address of the next element in the list as part of the list element. So let's start getting our terminology in better shape. We're going to call these things nodes. These are nodes in our list. And each node is going to keep in it some information. So for instance, coffee, and then the address where I can find the next item in the list. So if I hop to that address, I come to the next item in the list. This would be milk, and we have the element milk followed by the address of the next element in the list. And in this way, we can hop from one node to the next. It's important to think about huge amounts of data. If we only have a small amount of data, it doesn't much matter that we have to store it contiguously like this if it's in an array. But if we have a large amount of data, then we need to be able to use pieces of memory that are otherwise going unused. So you might have a few bytes here and a few bytes there. You can use these to keep your list. Let's look at the Java code for a node. This is the node class which we will be using. We will see that in each node we have an item, and this item is an object. It can be any object. So they don't all have to be the same type. They don't have to all be strings. You can mix them up as long as they are objects. And then following the item is next, which is also a node. This next is an address. So it's the address of the next node. This is our constructor. When we construct it with the item. It puts this new item into item, and it sets the next to be null. So when you create a node, the next is initially null. We'll talk about this constructor later, but this is primarily what we'll be using the first week. So if we go back to here, when we create a node, our next is initially null. And on a diagram, we symbolize null by a line across. So that is null. There's nothing in there. So we would put something in our first node with the address of the next node. So that address is where the next node is. Let's say it's here. On the board, we write it like this, or on a paper we write it like this, because putting the hex value of an address doesn't give us the same visual as this arrow does. So this is not an arrow that's in this next, but this is the address of where this node is in memory. So if I go to that place in memory, I will find this node, and there'll be something in there with the address of the next node. and there'll be something in there with the address of the next node, and this one has a null for the address, meaning that's the end of the list. I hope this helps to explain lists. It can be confusing at first, but the more examples we do, the clearer it will become.